All right, so in this video, we're going to take a look at some of the nuclear chemistry topics. And in the first one, we're looking at writing the symbols in a nuclear chemical equation. And in contrast to normal chemical equations, the nuclear chemical equations tend to be a little bit simpler, because all we really need to do is to make sure the numbers match up on both sides of the equation, right? So these are referred to as nuclear equations, again, to distinguish them from quote unquote normal chemical equations. So we'll take a look at a couple examples. It says, suppose a carbon-11 nuclide, and a nuclide is just another name for a radioactive isotope of an element. So carbon-11 nuclide decays into a boron-11 nuclide by emitting a positron. Complete the nuclear chemical equation below so that it describes this nuclear reaction. So we're given here the reactant, which is our carbon-11 nuclide, and then we're told that this decays into boron. So boron is B, and boron-11, so that means the mass number here is going to be 11. Now, we don't know what the atomic number is. Well, actually, we do, because we can look it up on a periodic table. So for boron, I have my table handy. That atomic number is 5. So that I can look up. Okay, so that's the atomic number of protons from the periodic table. So what I need to do now is to figure out what the other thing is that is going to be produced, or in this case, emitted in this equation. So it says that this is a positron that's being emitted. So what is the symbol for a positron? What is the mass of a positron? What is the number that goes in the bottom? All right, so we need to figure that out. If you look into the content for this week, we'll find the symbols for those. All right, and here we have several of them listed down here at the bottom. So we need to complete this equation. It says the missing thing here is the positron. So that'll be this one. So we have our E. The mass here obviously has to be 0. And then the number that goes as a subscript here has to be a positive 1. So the way that the math works is actually, again, really simple. What we need to make sure is that all the mass numbers, which we'll highlight in yellow, so whatever I add on the top here on the right side, 11 plus something should equal 11. In this case, 11 plus 0. And then the subscripts also need to add up. So 6 here on the left side is the sum of 5 plus whatever that is. In this case, it's a positive 1 that we will need. So when it comes to writing these nuclear equations, it really is just a case of doing a little bit of math, making sure the superscripts all add up to both sides of the equation, and also the subscripts add up. All right, so we have here our answer. In this case, you don't need to put the positive value in front of 1. Just 1 is understood, or the positive sign is understood. If it were negative, though, like in the case of an electron, you would need to include the sign there. So here is another example. So it says, suppose what do we have? An iron 58 nuclide transforms into an iron 59 nuclide by absorbing a neutron. Complete the nuclear equation. So it describes this reaction. So we're given the product, in this case, that nuclide that we have is iron, Fe, 59. Okay, and then the atomic number for iron is 26. You can look that up on the table, or we're given it here. And it says that iron 58 transforms into this. So we can write one of the reactants here. So iron 58, mass number will be 58. And if it's Fe, the atomic number has to be 26. So it transforms into iron 59 by absorbing a neutron. So absorbing means reacting with or combining with. The neutron here is this thing. So we'll have N. The mass there is 1. And the charge there on the bottom is going to be 0. So 26 plus 0 is going to give me 26. Those numbers match up. 58 plus 1 gives me 59. Those match up as well. that'll be your nuclear equation for that transformation, right? So again, making sure the numbers add up on the reactant side and the product side is key to solving these types of problems. All right, so this is just a sort of a derivation of the writing the nuclear equations. Here we need to balance the nuclear equation, and in contrast to normal chemical equations, we're not using coefficients and stuff like that. We're just trying to find the missing symbol in order to make sure that all the superscripts add up, all the subscripts add up as well. Okay, so I have my products. I have neon 22, atomic number 10, and then I have my E here, which is my positron, mass is 0, and then I have my 1 as my subscript. So again, making sure the numbers add up. So if I add up my masses, so I have 22 plus 0, so that should add up to give me 22 on whatever I have here on the left side, and 10 plus 1. Okay, so 10 plus 1 is going to give me 11. So that's going to go in the as the subscript. So what has atomic number 11? I can look that up on the periodic table. Atomic number 11 is going to be sodium. I have sodium here undergoing some sort of, in this case, it's a positron decay to form neon 22 and that positron. All right, so again, doing the math, again, it's not complicated math that we're doing, using the atomic number to identify what that element is. All right, so in this one, we're taking a look at the different modes of radioactive decay. So on the table, it lists information about the radioactive decay for 3 nuclides, and we need to fill in the missing information. So this is very similar to writing the nuclear equations, except now it's not written in an equation form or in a tabular form, but the idea is still the same. So for example, it says in the first one that our daughter nucleide or a daughter nuclide here is carbon 13. And we're also told that whatever we're starting off with here is undergoing positron emission. So that means it's emitting a positron. Well, what is a positron? Well, we already did that one. It's a E with the mass is 0, charge of 1. So again, all I need to do is to do the math. 13 plus 0 gives me 13. 6 plus 1 gives me 7. I can look up the 7, atomic number 7 on the periodic table, and that should be the atom right after carbon, which is nitrogen, N. And that's it. That's your missing nuclide in this example. And the second one, we're given the starting nuclide. We have uranium-238 and atomic number 92. It's undergoing some sort of a decay that we need to choose, and it says that the daughter nuclide here is thorium-234. And then 90 is the atomic number. So whatever I have here, okay, in order for the math to work, this 234 plus this thing should add up to 238. So obviously 234 plus 4 should add up to 238. And 90 plus something here should add up to 92. 90 plus 2 will add up to 92. So I just need to look up now what type of decay has a mass of 4, and then the subscript of 2. Looking at that is going to be our alpha particle or the helium nucleus. So we have He would fill in that. So again, the math there is what makes this work, both in the superscripts and the subscript. So for all of these, that's what you want to sort of turn it into an equation, nuclear equation, and then we can solve it. All right, so the last one here, we're looking at understanding the half-life for for radioactive samples, and the half-life for something is often abbreviated as T, subscript 1/2. And this is the time that it takes for half of the sample to decay. So undergoing radioactive decay. So we're given some information. It says a technician is working on 4 samples. Initially, each sample contains 13.00. So our initial amount in all of these is 13.00 micromoles of each of these samples of the radionuclide. First, order the samples by decreasing initial radioactivity, and then calculate how long it will take for the amount of radionuclide in each sample to decrease to 1/4 of the initial amount. So, a couple of things to note here. Our half-lives are given in hours and in, looks like in minutes. So in terms of the initial radioactivity, so the samples with shorter half-lives, you're going to have a larger initial radioactivity, or higher initial radioactivity. Okay, so what we're looking for here is to order the time from shortest time to longest time. Okay, so if I look at my values I have here, so 78 hours obviously is the longest out of these, so that will have the lowest initial radioactivity. The shortest time, we have to see I have 2 hours. I have 98 minutes, which is just over an hour and a half. 68 minutes, which is just over 1 hour. So 68 minutes is the shortest. That would be the highest initial radioactivity. Then 98 minutes, that's more than an hour, but less than 2 hours, that will be the second. And then the one left will be the third. Right, so we have those ordered. And then the next thing, which is the more challenging thing, is to figure out now the time for the amount of the radionuclide to decrease to 1/4 of the initial amount. So let's take a look at what this half-life actually means. So if I start with, let's say, 100 grams of something, if this sample undergoes one half-life, if one half-life has elapsed, after whatever time period that is, I will end up with 50 grams of the sample, right? So here I have 1/2 of the original amount. If another half-life is allowed to elapse, so another T 1/2, I will end up with 25 grams. Okay, so half now of the previous amount, which was half of the original amount. So here I have now this 25 grams. I have 1/4 of the original amount. Okay, so after 2 half-lives, 2 half-lives, I end up with 1/4 of the original amount. So in order for us to end up with this amount, 2 half-lives have to pass by. Okay, so we can work on it just from initial principles. Just think about, and it can start with any amount. It doesn't have to be 100 grams, but the math kind of works out a little bit easier here. Another way of thinking about it is if my initial amount is 1, let's say I had 1 gram initially. Okay, after 1 half-life, I would have 1/2 gram. And after a second half-life, I would have half of 1/2, which is 1/4 of a gram, right? So again, here we'd have 1/4 of the original. We would need 2 half-lives to elapse. So 2 half-lives, you know what the half-life length is. So 2 times 2 hours would be 4 hours. 2 times 78 hours will be, 100 and whatever 56 hours, etc.